In this video, we're going to learn a new technique of integration called integration by parts. And integration by parts has to do with the product rule from derivatives. It's the act of undoing the product rule. So let's first remember what this product rule was way back when we learned our derivatives. Remember, your product rule said that the derivative with respect to x of f times g is the first one times the derivative of the second plus the second guy times the derivative of the first. That was our product rule. And now notice that I can also go ahead and rearrange this just slightly. I'm going to put this derivative of f times g over on the right side, put this other stuff over on the left side, and I'm going to integrate both sides of this equation. So the integral of f times g prime plus g times f prime with respect to x will be equal to the integral of the derivative of the product. Well, we know that integrals and derivatives undo each other, so I just get f times g over on this right side. And now, since I know that an integral of a sum is the sum of the integrals, I can take one of these two integrals and move it to the other side of the equation. And then what we get from that is another formula. So what we get is the integral of f times g prime with respect to x is f times g minus the integral of g times f prime with respect to x. And what this is right here is our integration by parts formula, except that's not the standard way of seeing it. The way that usually we write this formula is if we let u equal f of x and g is going to be v. So u is f of x, v is g of x. Then we can rewrite this as the integral of u dv equals uv minus the integral of v du. And this formula right here is what's called the integration by parts formula, and that's the way most people tend to memorize it. I just wanted to show you that it does indeed come from our product rule. Now, the hardest thing with doing integration by parts is figuring out what to use for your u and for your dv. And then you can find your v by doing the antiderivative of dv, and you can find your du by doing the derivative of u. Now, in general, you want to choose u to be something that gets easier when you take the derivative. So the best way to learn integration by parts is to just do a whole bunch of examples. So that's what we're going to do. The rest of this video is just example after example. So here's our first example. Let's find the integral of x times sine of x dx. And now I want to point out that we could not solve this integral before using the techniques we already know. I know that the integral of a product is not just the product of the integrals, so I couldn't do a power rule on the x and then use one of my trig rules on the sine. It doesn't work that way. The only other thing we already knew was u substitution. But u substitution does not help us on this problem. If you chose u equals sine of x, your du would involve cosine, and I don't have a cosine in the problem. And if I chose u equals x, well, all that would do is turn this into the integral of u times sine of u du, and then we haven't changed anything. So this is why we need integration by parts, because sometimes substitution is not enough. So for integration by parts, you need to choose your u and your dv. And then you can find your du and your v by doing derivatives or antiderivatives appropriately. So remember, we usually want your u to be something that gets easier when you take its derivative. I have two choices. I can either use my x or I can use my sine of x. Well, even though the derivative of sine of x doesn't get more complicated, it doesn't get easier either. But if I chose u equals x, well, then the derivative of u would just be 1 dx. It got a little bit simpler because it's just a 1 instead of an x. So that means I'm going to choose dv as sine of x dx, and my v is going to be the antiderivative of sine of x dx. And that means that I'm going to get a negative cosine of x. So remembering my integration by parts formula, which I suggest you write down all of the time until you've memorized it, integral of u dv is u times v minus the integral of v du. So on this particular problem, my u was x and my dv was sine x dx. This should equal u times v. So that's x times negative cosine x minus the integral of my v du. So minus the integral of negative cosine x, that's my v, du is 1 times dx. Now notice I do have a minus and a negative in my integral, so I can rewrite that as just adding an integral. So where we're at right now, what we have right now is that this whole integral was equal to negative x times cosine of x plus the integral of cosine x dx. And that integral is something that we can do using our old rules. We know the antiderivative of cosine is sine. So when I do that, I get negative x cosine x plus a sine of x, and then plus your constant. And that is the answer to the original problem. So we've survived our very first integration by parts problem. It's not too terrible as long as you choose the correct u and the correct dv. If you choose the wrong one, you might end up getting something more complicated. And then I just suggest that you try it over again, choosing the other term as your u or your dv. So let's do another problem using this. Now, my next example isn't even going to look like it should be integration by parts when you first look at it. Because one clue that you want integration by parts is when it looks like a product. But this particular problem I'm about to put up doesn't look like a product. The integral of the natural log of x dx. This isn't a product, it's just finding the antiderivative of a natural log. But we don't know what that is. We can't think of a function right now whose derivative is going to be the natural log of x. We don't have that from our Calc 1 skills. But what we can do is integration by parts. It's just that we're going to want to choose the fact that we have a 1 being multiplied in here. We're going to use that 1 to our advantage. We need to choose a u and a dv. One of those things is going to involve the natural log of x. Now, I do not want to put natural log of x as dv, because if I already knew the antiderivative of natural log of x, I wouldn't even need to do integration by parts. I would just do the problem right away. So that means I need this natural log of x to be my u, and I know the derivative of natural log of x, it's 1 over x. So I get du is 1 over x dx. Now dv is just going to be my 1 times a dx. Antiderivative of 1 dx is just an x. So now when I do my integration by parts, integral of u dv equals uv minus integral v du. On this problem, my u dv is just natural log of x dx. U times v will be x times the natural log of x minus the integral of my v times my du. So x times 1 over x dx. Now notice over here, my x and my 1 over x, they cancel out. So I'm just going to have an integral of 1 dx. So let me rewrite that a little simplified. We have x times the natural log of x minus the integral of 1 dx. Then that antiderivative of just the integral of 1 dx will get me an x. And then don't forget your plus c. And that is going to be the antiderivative of the natural log of x. Not something you probably would have guessed just using your Calc 1 skills. Now, anytime you're doing integration by parts, if you don't trust your answer at the end, you can always check your work by taking the derivative of your answer. If you get back to where you started from, you did it correctly. So let me just quickly check this one to help convince you that this procedure works. Let's take the derivative of our answer. X natural log of x minus x plus c. The derivative of x natural log of x needs a product rule. That's the first guy times the derivative of the second, so x times 1 over x, plus the second guy times the derivative of the first guy, natural log of x times 1. And then my derivative of a minus x is minus 1. Derivative of a constant is 0. X times 1 over x is 1. So this one and that minus 1 subtract away. And all I have left is natural log of x, which was the original thing we were integrating. So this did indeed work. You can just check your answer by taking a derivative to make sure it worked out correctly. Let's do some more examples. Let's find the integral of t squared times e to the t dt. So I'm going to want to use integration by parts again because substitution does not help me here. If you tried to do substitution with u equals t squared, it's not going to work. Or u equals e to the t, that's also not going to work. So we're stuck unless we use integration by parts. So we need to pick a u and a dv, and then find our du and our v from this. Now the question is, what do we want to choose for u and what do we want to choose for dv? And remember, if at all possible, it's usually best to choose your u so that it gets easier when you take the derivative. So in this case, I would choose u equals t squared, because then the derivative gets a little bit easier, 2t dt. It's a little bit simpler because the power is now 1 smaller. For dv, I would choose e to the t dt, because even though it's not getting any easier when we take an antiderivative, it's not any more difficult either. Antiderivative of e to the t is itself. So then remember the formula. Integral of u dv equals uv minus integral v du. So I have the integral of t squared e to the t equals u times v. So that's t squared e to the t minus the integral of v times du. So I'm going to write that as 2t e to the t dt. So now take a look at what we got. We got this part here, t squared e to the t is already integrated. Now this guy, 2t e to the t dt. Can I integrate that? Well, unfortunately, I can't integrate it just straight away. And also, substitution doesn't work on that guy either. But what can we do with that? We can do integration by parts again. Yes, sometimes you have to use integration by parts more than one time in a problem. So let's go ahead and just try it again. Let me rewrite where I'm at. We have t squared e to the t minus 2 times the integral of t e to the t dt. So I need to pick a new u and a new dv to figure out that integral. So I would do the same sort of thing I did on the last one. I know if I choose u equals t, then the derivative will get a little bit simpler. I'll just get 1 times dt. If dv is e to the t dt, then the antiderivative of that is just e to the t. So now I can use my formula again. Remember, it's going to be u times v minus the integral of v du. Now just be careful because in front of this integral I have a minus 2. So I personally would write down what I had before, t squared e to the t minus 2, and then put a giant parenthesis and do my whole uv minus v du over there, and then close my parenthesis up. So u times v is t e to the t minus the integral of v du, e to the t dt. Now I would go ahead and distribute this minus 2. I get t squared e to the t minus 2t e to the t plus 2 times the integral of e to the t dt. So I still have one more integral to go, but at least the antiderivative of e to the t is itself, and then we'll be finished. So to finish the problem up, I just have to do that very last antiderivative, and then don't forget my plus c at the very end. So we will get t squared e to the t minus 2t e to the t plus 2, then the antiderivative is e to the t, add your constant, and that is the answer to the original integral. So I think integration by parts is quite a bit of fun. Sometimes it's a bit of a puzzle trying to figure out what u and what dv are, but once you get the hang of it, it actually ends up being kind of fun. Let's do another example. I know my students usually really don't like problems that have a lot of trig in them, so I'm going to do one with some trig, try to get us a little more comfortable with that. So let's see. For this example, let's do an integral of e to the x times sine of x dx. So we're going to do integration by parts again because I have a product and using u substitution does not help here. I'm going to need to choose a u and a dv. Now this problem might scare you for a little bit because neither of the choices gets easier when I take the derivative. Derivative of e to the x is itself, and derivative of sine is cosine. Neither one gets more complicated or easier. So which one do we choose? And when I'm in a situation like that, I tend to just keep them in the order they're already listed. So I would do u equals e to the x and dv equals sine of x dx. It would work the other way as well. But if I do u equals e to the x, then du is e to the x dx. If dv is sine of x dx, then v is going to be a negative cosine of x. So now, using my formula, remember, integral of u dv equals uv minus integral v du. And fill in all of this information. I'm going to have the integral of e to the x sine of x dx is u times v, so that's negative e to the x cosine x, minus the integral of my v du. So I'm going to have a negative cosine x and e to the x dx. Now, of course, having a minus negative, we can rewrite that as just adding the integral. So let me rewrite this right now. So I have negative e to the x cosine of x plus the integral of, I'm just going to write it as e to the x cosine x dx. So take a look at what we have over here. We're going to need integration by parts again. It worked for us on the last problem, so maybe it'll work again this problem. So I need to choose a new u and a new dv. Now, I would suggest that when you are doing problems where you integrate by parts more than one time, stay consistent with your choice of u and dv. So since I chose u equals e to the x last time, I'm going to stick with that this time. If you don't stay with the same thing you chose before, sometimes really crazy stuff happens where you end up right back where you started from and you've lost everything else. So I suggest that you stay consistent to eliminate some of those problems. So I'm going to have u equals e to the x and dv equals cosine x dx. That will make du equal e to the x dx, and v will be the antiderivative of cosine, which is sine. So now if I write down where I'm at, we had negative e to the x cosine x, and then plus, it's going to be uv minus v du. So I have u times v, e to the x sine x, minus the integral of v du. So that's an e to the x sine x dx. Now at this point, some of you are going to be a little bit concerned because look at that. We're going to need integration by parts again. How many times do I have to do integration by parts on this problem? And some of you might even notice that e to the x sine x, that's what we had at the very beginning of the problem. And that's correct. When something like this happens, don't keep doing integration by parts over and over again. You're never going to be able to stop. It will just keep going forever. So when you get the exact same integral that you started with, we have to do something a little bit clever. We didn't do anything wrong. We just have to remember what this whole thing is equal to. So what we have done so far is we have found that our original problem, integral of e to the x sine of x dx, this is equal to negative e to the x cosine x plus e to the x sine x minus an integral of e to the x sine x dx. So I have this equation here. Now, what would happen if I take this minus integral of e to the x sine x and I just add it to the other side of the equation? Well, then I would have two integrals of e to the x sine x over on this left side. So let's do that. Let's add this integral to the other side. That gives me 2 times the integral of e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x. Now, what we wanted to solve for in this problem is this integral over here, just without a 2 in front of it. So let's just use our algebra skills. Just divide both sides by 2 and we'll have the answer. When I divide both sides by 2, I get that my original integral is equal to, I'm just going to write it as 1/2 times this other side. Negative e to the x cosine x plus e to the x sine x. And then just don't forget that you should have a plus c at the very end. And there is the problem. So on some of these integration by parts problems, you have to just use the formula once. Sometimes you have to use it more than once. Other times you have to use it more than once and then do some algebra to get the answer by just moving integrals to the other side of the equation. So there's a lot of different things that can happen in these problems, and you just have to get a lot of practice with all of them. So all that we've done so far has been indefinite integrals using integration by parts. So the indefinite ones are the ones that don't have bounds of integration, and you end up with that plus c at the end. But just because I haven't done a definite integral yet doesn't mean that we can't use integration by parts with definite integrals. We absolutely can. So my next example is going to be a definite integral. Let's do an integral from 0 to 1 of tangent inverse of x dx. And I do want to put a little note to all of you here that tangent inverse is the same thing as arctangent of x. So depending on what notation you prefer, you might be used to seeing this one way or the other, but they're both the same function. I personally prefer the inverse notation rather than the arc notation, but either way works just fine. So this is one of those problems where it doesn't look like you need integration by parts because I don't have a product, but we do need it because I highly doubt that you know the antiderivative of tangent inverse. But you should know the derivative of tangent inverse from your Calc 1 skills. So I'm going to let u equal tangent inverse of x, and then my dv will just be my dx. The derivative of tangent inverse is 1 over 1 plus x squared. And my antiderivative of just a 1 dx is going to be x. So, using my integration by parts formula, I know that my integral from 0 to 1 of tangent inverse of x dx, that's going to be u times v minus integral of v du. And then we just have to remember we have bounds to plug in. So my u times my v is x times tangent inverse of x, and we would need to plug in bounds of 1 and 0. And then I have my minus integral from 0 to 1 of v du. So x over 1 plus x squared dx. And I would go ahead and plug these bounds in right now to simplify the beginning part before we deal with that other integral. So if I plug in the 1 and plug in the 0 for just that uv part, I'm going to have 1 times the tangent inverse of 1 minus 0 times tangent inverse of 0. And then I still have my other integral, minus the integral from 0 to 1, x over 1 plus x squared dx. So 1 times the tangent inverse of 1, what's that going to be? Well, I'm going to end up with a pi over 4, because tangent inverse of 1 is pi over 4. Then the 0 times tangent inverse of 0 is just going to be 0. So I get pi over 4 minus the integral from 0 to 1 of x over 1 plus x squared dx. So now if I just finish up this last integral, we'll have the answer. But how do I do that last integral? Do I need to do integration by parts again? Well, the answer to that is no. Actually, just a simple u substitution will work for this integral. If I let my u equal the denominator, then I can do just simple substitution to figure that out. So let's do substitution. Let u equal the denominator. That means du will be 2x dx, which means that dx is du divided by 2x. And then I'm also going to change my bounds of integration. When x is 0, that means that my u is equal to 1 plus 0 squared, which is 1. And when x is 1, my u is 1 plus 1 squared, so that's 2. Rewriting using this substitution, I'm going to get pi over 4 minus an integral from 1 to 2. I have x, u on the bottom, and dx is du over 2x. Notice those x's cancel out, and I can pull the 1/2 outside. So when I do that, we have pi over 4 minus 1/2 times the integral from 1 to 2 of 1 over u du. That's going to get me a natural log. I have pi over 4 minus 1/2 natural log, absolute value of u, plug in the 2 and plug in the 1. Now when I plug in the 2, I'm going to get a minus 1/2 natural log of 2. When I plug in the 1, I would have a 1/2 natural log of 1, but the natural log of 1 is 0, so I don't need that part. So we just get pi over 4 minus 1/2 natural log of 2. I dropped my absolute values at the end because the absolute value of 2 is still 2, so this is perfectly acceptable right there. And you could write the answer in different ways if you wanted to. Like you could move this 1/2 up as an exponent to make it a natural log of the square root of 2 if you wanted. But I personally would leave my answer right there. All right, so there's an example of how you do integration by parts with a definite integral. It's really not any different. You just have to make sure that you plug the bounds into the uv part, as well as keep it on the integral of v du part. So I hope you enjoyed this intro to integration by parts. Now you can expect to see all sorts of integration by parts integrals in all of our future videos. So you should always be ready to pull this out, just like we're always ready to pull substitution out. If you have any questions, feel free to drop them below. If you're a current student, you can also ask me in person or through email or office hours. And I will see you guys next time.